In this video, we are going to talk about triangles and quadrilaterals and their properties. More specifically, midsegments and medians. Midsegments and medians are different ways to split apart polygons. We're going to make some conjectures, which means basically make some theories about these breakups of the polygons, and then we're going to test them. We can try to give some examples to support our conjecture, or we can, if we see that it's not true, the conjecture is not true, we can provide a counter example. So first, let's define what a midsegment is. A midsegment is made by taking the points of two adjacent sides. That means, adjacent means they're beside each other. And draw a line segment to connect the midpoints. Okay, so we need to start with the shape. Let's start with the quadrilateral. Okay, so we have basically a quadrilateral here. The lines aren't perfect, but it gives you the idea. And if you want it to be perfect, you can use a straight edge or a ruler. Or if you're drawing here in paint, you can also use a line tool to make a straight line. So the midsegment is made by taking the midpoints of two adjacent sides. So we want to take the midpoints. So we can use a ruler and measure out a length. So say we're trying to measure between this point and this point, and we use a ruler. We could find the midpoint to be right here. And we want to take the midpoints of two adjacent sides. So this side here, we've already done. Now we need another side that's adjacent, another side that's beside. So let's do this one here. Okay, we use a ruler and we measure, and it'll be right here. So you can see that what I'm doing right now, I haven't used a ruler and I haven't used straight edges, but you can absolutely do that on paper, so please do. And then we're going to connect it. So here's a way to show that we did a midpoint, and here again that this was a midpoint, and we connected it together. We could continue to do this for all of the sides of this quadrilateral. We can continue to find the midpoint and the other midpoint. And draw all the midsegments inside the quadrilateral. Notice how it also formed a quadrilateral? Okay, let's talk about some of these words. Counterexample. So a counterexample is an example that disproves a theory or conjecture. So basically, you're giving an example that shows that someone's wrong or that an idea is wrong. Okay? So conjecture. Someone can make up this theory, this idea. Conjecture. The midsegments of a rectangle form a square. Well, down below we have this rectangle, and you can easily see that when you make these midsegments, they are not forming a square. We know that because there's a 53-degree angle here, and a square would have to have all 90-degree angles. So this picture, this drawing, is a counterexample. It disproved. So an example could help to support a conjecture. So if I thought that this was true, midsegments of a rectangle form a square, I could start making some exact drawings on grid paper and try to come up with some examples of rectangles where the midsegments form squares. And if I was able to make drawings where the midsegments were squares, then that would be supporting the conjecture. It wouldn't be a proof. A proof would have to show that it's always true for every rectangle in the whole wide world. Well, I can't draw every single rectangle in the whole wide world. That would take me my whole life and it would keep going because rectangles could be any possible size. So just making a specific example is not enough to prove, it's just enough to support, to show a bit of evidence that the conjecture is probably true. On the other hand, you only have to give one example that doesn't work to disprove. Only one counterexample is needed. Okay, so I'm going to give you an example here that's not a math example at all, just so you understand the terminology better, hopefully. So, if I make a conjecture, all female blondes like pink. I could make some supporting examples. I am a blonde, and I like pink. So that's support. I ask someone else. Audrey's a blonde, and she likes pink. That's a supporting example. So they match the conjecture, they support it. Some blondes like pink. It hasn't shown that all female blondes like pink, but some do. To disprove it, we just need one example. So I asked my friend Brianna. Brianna is a female blonde, and she does not like pink. So this example, Brianna doesn't like pink. This disproves the conjecture. So Brianna is a counterexample. Brianna disproved it. All female blondes like pink. Well, in the set of all female blondes, who like pink, Brianna's over here. She likes purple. She does not like pink. So someone doesn't like pink, not all female blondes like pink. That's the idea of a counterexample. Sometimes it's actually easier to disprove something than to prove it. Now, if we go back to this example we saw up here, the conjecture was the midsegments of the rectangle form a square. And we could see right away it didn't form a square. But if we look at this shape, we can see it does form a parallelogram. And I think it actually forms a rhombus. Look at the lengths here. They all seem to be over 3 and 1.5. Over 3, 1.5. I think it actually forms a rhombus. So we could make a conjecture. We could say the midsegments of a rectangle always form a parallelogram, or the midsegments of a rectangle always form a rhombus. It is very tough to prove it, but you're often asked to support your conjecture with examples or provide a counterexample. So if we want to show that it's true, we really think it's true. So let's try our best to draw some rectangles. And we're going to try to show that no matter what the shape of the rectangle, the midsegments I still want that this color. The midsegments form, oh, well, I was just saying parallelogram, but in the question I already typed rhombus. So let's try to show it forms a rhombus. Okay, so this length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's great. I don't even need a ruler. 1, 2, 3, 4, 5 is the mid segment. And here 1.5, 1.5, 5. Let's draw some lines. So mid-segment, 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 and mid-segment. Okay, how do we even know whether this is a rhombus or not? Well, a rhombus has very specific characteristics. A rhombus all four sides are equal. And we also know that opposite sides are parallel. There's a shortcut for saying parallel. We go like that. Opposite sides are parallel. So let's figure out these lengths. If you have a ruler, you can bring your ruler up and measure it. If you're in GeoGebra, you can measure it. But unfortunately, right here in Paint, I don't have those tools. I could get a ruler. That would absolutely work. But I can use the grid to help me too. So notice that this is down 1.5 and over 1, 2, 3, 4, 5. So it has a certain length to it because of that. It would be easier just to measure with a ruler. You can see that this length is equal to this length. Make your drawing, make your own rectangle, get out a ruler, and you can see that definitely all of these sides are equal length. Now we need to show that they're parallel. Well, it's really easy to show that they're parallel because we're on a grid. All we need to do to show that two lines are parallel is to show that the slopes are the, I hope you said same. So let's do the slope. It's kind of helpful. We already have the slope right here. So up 1.5 over 5. So the slope of this line, actually we should say it's down, I'm sorry about that, down 1 over 5. And the slope of this one is up 1.5 and over 5. I missed the half. Okay, let's do the slope of this piece here. This one is down 1.5 and over 5. And the slope here is up 1.5 and over 5. Up 1.5 and over 5. Okay, usually for final answers we don't put decimals and fractions together. Usually we would write this, multiply the top by 2 to make it a whole number, make it 3, and the bottom a whole number. So usually we would give an answer like 3 over 10. But right now we're just trying to show that the slope's equal, so I'm not too worried about proper mathematical form. I just want to show the opposite slopes are equal. So this slope and this slope, they're opposite sides from each other and they are parallel. And this side, they are opposite each other and they are parallel. Great. Notice that you can also use the points if you have it on a grid system, and if you defined the axes, you could label each of the points. So say you had the axes here and here, it can be helpful to say this point is 1, 2, 3, 4, 5.5. Sorry, x0, y 5.5. So it can be helpful to list out all the points. And then you could use the points to find the slope if you needed to. But luckily our grid was nice enough here that we could figure it out just using the grid. Okay, so this example of this rectangle that was 3 by 10 helped to support that the midsegments of a rectangle form a rhombus. We didn't prove it, but we did help to support it. Let's do another example. Okay, let's talk about medians now. So a median goes from the midpoint of one side to the opposite vertex. We talk about medians when we're talking about triangles. Conjecture. The median of an isosceles triangle formed by, I have to correct that for you guys, formed by taking the midpoint of the non-equal side is perpendicular to the non-equal side. Okay, so let's start off just by making a sketch. So, isosceles triangle. That's what we're dealing with here. Let's get that sketched out. Okay, so the median of an isosceles triangle formed by taking the midpoint of the non-equal side. So I made it so the side here on the left is equal to the side here on the right, and the one on the bottom is not equal. Okay, so that bottom one is the non-equal side in the question. The midpoint of the non-equal side. Okay, it's very easy to see here that the midpoint is right here on the grid because it's a length of 4 and we're right in the middle. Okay, and we're trying to make a median. So the median goes from the midpoint to the opposite vertex. Okay. It is perpendicular to the non-equal side. So this example we just made right here clearly shows that these lines are perpendicular because they're on the outer grid. You could find the slope of each line to show they're perpendicular. Remember that the slopes are negative reciprocals, but it's very clear in this case. So if you were asked to support the conjecture, just giving an example is enough. If you're asked to prove the conjecture, it's a lot more work. Now we could actually prove this one. This one's not too bad. So if we think about it, isosceles triangles have these angles in here that are equal. And then we have one more angle up here. Let's call it B. So we did A and A because they're equal, and now we have an angle B. So we know that the sum of the interior angles is equal to 180. So A plus B is equal to 180 degrees. Now we're trying to show that an angle inside here, we're trying to show that that would be equal to 90. Prove angle C is equal to 90 degrees. Okay? So we can start off with A plus B is equal to 180. So we have 2A plus B is equal to 180. All right. Now we have a second triangle. We were talking about the big outside triangle before. Now we have this triangle here that was formed by taking the median. And for that triangle, we see that A plus this smaller piece is half of B over 2. So A plus B over 2 plus C, if we add up all these angles, it would also be 180. A plus B over 2 plus C is equal to 180. So what I'm doing right here, it's not really something that you're expected to be able to do in grade 9. In grade 10, you should be able to do this. So we're looking ahead a little bit at some higher skills. So we're going to try to use these two equations to figure out if C is equal to 90 degrees. Okay. So here we have, I'm going to get B by itself. I'm going to isolate the B. I'm going to move this 2A over to the other side. Okay. And did a little bit of work here. I don't think it's really necessary to do it. I'm just going to get rid of it. Okay. Now I have some information about B. I'm going to put that information into our other equation. We know that B has to be 180 degrees minus 2A. So I put that in for B, and it's all over 2, plus C is equal to 180 degrees. Okay. Let's simplify here. 180 degrees minus 2A, that's all divided by 2. So we can have 90 degrees minus A. So I divided 2 into both things, because everything's divided by 2. Plus C is equal to 180 degrees. Okay, we have A minus A, they're like terms, and they cancel each other out. So we just have 90 degrees plus C is equal to 180 degrees. We can isolate this C by moving the 90 over, so subtract 90 from both sides. C is equal to 90 degrees. So C is equal to 90 degrees, which means for sure the median is perpendicular to that non-equal side. Okay, so we actually proved this one. A little bit more tricky than just giving an example, right? This one we're just going to do a supporting example. An exterior angle of a triangle is equal to the sum of the two interior angles opposite of it. Okay, so we're going to draw a triangle. I'm going to try to make this one a really easy triangle so that we can know some specific values about it. Okay, so I purposely made this triangle an isosceles triangle, so these two inside angles are equal, very easy, and it's easy to see all of these angles. So I can see right away that this is supposed to be 45 because it's a 90-degree angle broken in half, and this one's supposed to be 45, and this one is a 45 and a 45. This one's a 90-degree angle. Okay. So we've studied exterior angles before, and we've studied a straight line broken into two angles. A straight line broken into two angles is called a supplementary angle, and these have to add up. So this angle right here has to be 180 degrees, which is the whole line, minus the section of the other piece, which is 45 degrees. Okay, so 180 degrees minus 45. I like to do 180 minus 40 is 140, and then minus another 5 is 135. Okay, so this is some information we know about this triangle, and we're trying to support that the exterior angle is equal to the sum of the two interior angles opposite it. So here are the two interior angles, and what do they add up to? Well, they add up to 90 degrees plus 45 degrees. Okay, so 9 and 90 and 40 is 130, and then another 5, 135 again. That's great. So we just supported the conjecture because that exterior angle is equal to the sum of the two interior angles opposite it. And this is always true for any triangle. It's very handy. Okay, our final conjecture that we're going to look at and try to support is the length of the midsegment in a triangle equals half of the length of the side opposite it. That sounds like quite a bit. So let's draw this out. So we're going to do a triangle. Hey, you know what? In Paint, I have a triangle tool. Why am I working so hard to make a triangle when it can make it for me? All right. I'm purposely making this one so it matches on the grid nicely. So we are going to try to support this. We're not going to try to prove it, we're going to try to support it. The length of the midsegment in a triangle equals half of the length of the side opposite to it. Okay, so we need some midsegments. This line, let me just sketch this out and make sure it works. So I think the midsegment's going to be right here. Notice that we can go up 2 and over 2 and get to this point, up 2, over 2 and get to this point. So definitely our midpoint is here. Okay, and on this side, same thing, up 2 over 2, up 2 over 2, our midpoint. Let's draw the line. Not any line, this line's called a midsegment. Great. So in this case, we've made it match up nice on the grid and we can actually just count out the length. 1, 2, 3, 4. This is a length of 4 units. And at the bottom, 1, 2, 3, 4, 5, 6, 7, 8. This is a length of 8 units. Okay. The length of the midsegment in a triangle equals half of the length of the side opposite to it. Okay, so 4 is half of 8. The midsegment here, and this is the side that's opposite. So we've just supported that. Now, I drew a fairly special triangle. It's an isosceles triangle, and it has these nice, beautiful 45-degree angles and a nice 90-degree angle at the top vertex. So it's possible that it's just a coincidence that it works perfectly for this triangle. If I drew some more triangles that are not so nice, and I tried to do the same steps with them, it would really give me a better idea of whether or not this prediction is true. So if we just quickly midway is here, 1, 2, 3, 4, and over 1, so halfway is down 2. A little bit difficult to calculate this, but it looks like this number's a little bit hard to do, but it's definitely going down 1.5 and over 1. This is down 3 over 2. There's a good chance that this midsegment is actually half of the length of the opposite side. It really does look like it, doesn't it? Now, to prove it, we would have to be more exact. We could use things like the interior angles, make congruent triangles. There's definitely things you can do to prove a conjecture like this. But if we're just trying to support it, then this is all we need to do. And notice when we start drawing triangles that were not as pretty and nice, there's a good chance at that point you're going to find a counterexample, but we didn't happen to find a counterexample here.